Hello, my dear students. In the last class, I discussed about long column subjected to axial loading. Today's class, I will be discussing about when the column is subjected to eccentric loading, means it is not loaded at the center. In many cases, we have referred when the load acts axially on the column. That is, the line of action of the load coincides with the axis of the column. Means the load is acting exactly at the axis center of the column. But in actual practice, what happens, it is not always possible to have an axial load on the column, and eccentric loading takes place. Here we will discuss the effect of eccentric loading on the Rankine's and Euler's formula for long columns. Okay, so for this there is derivation is there, that is not important. So you just remember, in the case of eccentric loading, the maximum bending moment can be calculated by using this formula. That is, M maximum is equal to P into E into secant LE divided by 2 into square root of P divided by EI. P is the load and E is eccentricity, and LE is effective length, and P is the load, E is Young's modulus, and I is moment of inertia. So if you have all this data, we can calculate what is maximum bending moment. After that, you have to calculate what is the maximum stress. In the case of long columns, that is compressive stress. So maximum compressive stress is given by this formula, that is sigma max equal to P divided by A plus M divided by Z. So here in the when we substitute this M in this equation, P divided by A plus, this is substitute M is equal to PE secant LE divided by 2 square root of P divided by EI divided by Z. Okay, so this is the formula you have to remember. And here L effective, that is based on the end conditions. There are 4 end conditions. So based on the given end condition, you have to write what is L effective. In the here there is one note you have to remember. In case of short column, that is with no buckling, the maximum bending moment is given by M maximum is equal to P into E as compared to the column M maximum. In the case of long columns, maximum for the eccentric loading, maximum bending moment is given by this formula, P into E into secant of LE divided by 2 into square root of P divided by EI. But in the case of short column, what happens? Maximum bending moment is given by P into E. That's it. Only the load multiplied by the eccentricity. Okay, that is the difference between short column and long column in the case of eccentric loading. Let us take one example on this. An alloy hollow circular column of 200 mm external and 160 mm internal diameter is 5 meter long and fixed at both of its ends. It is subjected to a load of 120 kN at an eccentricity of 20 mm from the geometrical axis. Determine the maximum stress induced in the column section. Take E as 120 GPa. Okay, here this is a hollow circular column. Okay, so capital D is given, that is 200 mm, and small d internal diameter, that is 160 mm, and length of the column is 5 meter long. So let us convert into millimeter. So that is 5 into 10 raised to 3 millimeter, and load is P is equal to 120 kilonewton. So 120 into 10 raised to 3 Newton, and eccentricity is equal to E, that is equal to 20 mm, and modulus of elasticity E is equal to 120 GPa, or 120 into 10 raised to 3 Newton per millimeter square. Okay, we have to use that formula. For that we required A and I. So first we'll calculate what is the area of the column. For the hollow circular section, area is equal to pi divided by 4 into capital D square minus small d square. Substitute what is capital D and what is small d. So that is pi divided by 4 into 200 square minus 160 square. So you get 11.31 into 10 raised to 3 millimeter square. This is area. Now let us calculate what is moment of inertia I, that is equal to pi divided by 64 into capital D raised to 4 minus small d raised to 4. Substitute capital D is 200 and small d is 160. You get I is equal to 46.37 into 10 raised to 6 mm 4. Now we have that formula, that is this is the formula, P into E into secant LE divided by 2 into P divided by EI. Okay, so for that we required modulus of section also, that is Z. Z is equal to moment of inertia divided by Y maximum. I divided by Y maximum. This is a hollow circular section. So that is I divided by Y maximum is capital D divided by 2. So that's why section modulus of section is given by I divided by D by 2. Okay, so I is equal to calculated value, that is 46.37 into 10 raised to 6 divided by capital D, that is 200 divided by 2. Okay, simplify this, you get 463.7 into 10 raised to 3 millimeter cube, because this is section modulus I divided by Y maximum. Okay, now here the column is fixed at its both the ends. It is given, so equivalent length of the column LE is equal to L divided by 2. What is L? L is equal to 5 into 10 raised to 3 divided by 2 is equal to, simplify this, you get 2.5 into 10 raised to 3 mm. Now let us calculate this. What is LE divided by 2 into square root of P divided by EI, because this is the equation right here. Secant of this you have to calculate. So let us calculate first that LE divided by 2 into square root of P divided by EI. Substitute what is LE? LE is equal to 2.5 into 10 raised to 3 divided by 2 into square root of P is 120 into 10 raised to 3. It is given, load is equal to 120 into 10 raised to 3 divided by E into I. E is 120 into 10 raised to 3 Newton per millimeter square into I. I is calculated value, that is 46.37 into 10 raised to 6. So substitute, simplify this, whatever the answer you get, that is in radians, because that formula is secant of this. So the answer is radians, so you have to convert into degrees. How you can convert radians into degree? Multiplied by 180, whatever the answer you get, multiplied by 180 divided by pi. Okay, so this answer you get 0.1836. So multiplied by 180 divided by pi, you get 10.52 degree. Okay, this is your answer. Now let us substitute in the equation. What is that equation? Sigma maximum is equal to P divided by A plus PE secant of LA divided by 2 into square root of P divided by EI divided by Z. So this is the given equation. So substitute here what is P is equal to 120 into 10 raised to 3 divided by A. A is calculated value, that is 11.31 into 10 raised to 3 plus PE. P is 120 into 10 raised to 3 into E. E is given eccentricity, that is 20 mm. So substitute 20 this here into secant of this. This we have calculated here, that is 10.52 degree. So secant of 10.52 degree divided by divided by Z, this equation. I am considering this equation. Z is equal to 463.7 into 10 raised to 3 Newton. Simplify this, you get sigma maximum is equal to 10.61 plus 5.26, that is equal to 15.87 Newton per millimeter square, or 15.87 MPa. This is they have asked to calculate the maximum stress induced in the column. So maximum stress is given by this equation. So that's why you have to use this equation. Okay. This is the maximum bending moment equation. If it is asked to find only maximum bending moment, have to use this, but here it is asked to calculate stress, so you have to use this formula: P divided by A plus 1 divided by Z into P into E into secant of this term. So first, how to do this? First calculate this and convert it into degrees, and then substitute secant of this. Okay, then all other terms are simple, direct substitution. So you get what is maximum compressive stress. In this way, you can calculate what is the maximum stress induced in the column when it is subjected to eccentric loading. I hope all of you understood. Thank you.